Somewhere out there, space itself might be folded over, with a shortcut punched straight through it. A tunnel that could connect here to a galaxy billions of light years away. Step in one side, out the other, and skip the entire universe in between. A cheat code for reality. So today, what if you fell into a wormhole? Where would you come out, and would there be anything left of you to enjoy the view? Spoiler! The view is spectacular. You are the problem. First, what actually is a wormhole? Picture a tunnel with two ends, two mouths, joined by a throat. To see why that's useful, think of all of space as a giant rubber sheet. Two places can sit light years apart on its surface. But fold the sheet over, and those 2 points can be brought right next to each other. Punch a tube between them, and you've built a shortcut. That tube is the wormhole. Now, this is not a black hole. A black hole is a one-way door with a very rude bouncer. Fall in, and you are never coming out. A wormhole, in theory, is a hallway with a door at each end. The name comes from the physicist John Wheeler. Picture a worm in an apple. To reach the far side, it could crawl all the way around the skin, or simply bore straight through. That shortcut is the wormhole. Physicists, naming the fabric of reality after fruit. Bold choice. To understand how a tunnel through space could even exist, we first have to talk about gravity. Because gravity is far stranger than it looks. In 1915, Albert Einstein realized that gravity isn't really a force at all. It is the shape of space itself. Mass tells space how to bend. A star, a planet, even you, presses a dent into the fabric of the universe. And what we feel as gravity is simply things rolling along those curves. But if space can bend, it can do far more than dent. In principle, it can fold, it can stretch, and it can even be torn. In 1935, Einstein returned to the idea with Nathan Rosen. Buried inside the equations for a black hole, they found something extraordinary. A bridge leading to another region of space entirely. So why would bending space create a shortcut? Picture an ant crossing a sheet of paper. The long way runs all across the surface. But fold the paper over, and the ant can simply step across the gap. Gravity is what folds the paper. There was just one problem. This first bridge was useless. It pinched shut so quickly that not even light could slip through. Einstein found a tunnel through reality and basically filed it under neat, but probably pointless. To keep one open, you would need something far stranger. So the first wormhole was a dead end. To get a useful one, we have to sort the bad tunnels from the good. The simplest kind, hidden inside a black hole, is called a Schwarzschild wormhole. And it is hopeless. It collapses the instant it forms, crushing anything inside. The worst hallway in the universe. Then, in 1988, the physicist Kip Thorne found something better. He was helping the astronomer Carl Sagan with a science fiction novel and ended up inventing the traversable wormhole. A tunnel you could actually survive. The trick is keeping the throat open. Normally, gravity wants to slam it shut. To fight back, you need something with negative energy. Physicists call it exotic matter. Negative energy sounds made up. But it's real. Put two metal plates incredibly close together in a vacuum, and the space between them ends up with less than nothing in it. It's called the Casimir effect, and we have measured it. The catch is scale. To hold a wormhole open, you'd need roughly a planet's worth of the stuff. We can currently produce about enough for a very sad sandwich. So a traversable wormhole isn't forbidden by physics. It's just an engineering project of truly ridiculous size. All right. Say we somehow build a giant, traversable wormhole. Could you actually survive the trip? This is where it gets personal. The first danger is gravity itself. Near a small wormhole, your feet are pulled far harder than your head. The difference stretches you, thinner and thinner, into a long strand of atoms. Physicists genuinely call this spaghettification. The fix is size. Make the wormhole big enough, light years across, and the stretching becomes so gentle you would never feel it. So pack light. But pack for a very long trip. Then there's light. As radiation falls into the throat, it piles up and shifts to higher energy until a calm glow becomes a lethal blaze. You could be cooked by the accumulated light of the entire universe. But if you made it through, the view would be unlike anything in existence. The sky bent into rings, the stars of two different regions smeared together, and the exit growing in front of you like a window into somewhere new. So, survivable, in theory. Just bring sunscreen rated for the heat death of the universe. Now for the part that broke physics. A wormhole might not just be a shortcut through space. It could be a shortcut through time. Here's the trick. Take one mouth of the wormhole and fly it around at nearly the speed of light. Relativity says moving clocks tick slower. So when you bring it back, the two mouths no longer agree on what time it is. Step into the mouth that aged slowly, and you could step out of the other, into the past. You've just built a time machine out of a tunnel. Which raises an awkward question. If you could reach the past, what stops you from changing it? The classic version, what if you stopped your own grandparents from ever meeting? Physics has a few answers. One idea, called Novikov self-consistency, says the universe simply won't let you. Any trip to the past was always part of history. You can't change it, because you never did. Stephen Hawking went further with what he called the chronology protection conjecture. The laws of physics may actively forbid time travel to keep history safe for historians. For now, no one has ever seen time travel happen, which is either deeply reassuring or a little disappointing. So could we ever actually build one? Honestly, not anytime soon. The numbers are staggering. To prop open a human-sized wormhole, you'd need the negative energy equivalent of a planet like Jupiter, turned entirely into the strangest stuff in physics. We can currently make a few atoms worth for a fraction of a second. So maybe we don't build one. Maybe we find one. A natural wormhole, left over from the chaos of the early universe, drifting quietly somewhere out there. How would we spot it? A wormhole would bend passing light in a very particular way, and might even reveal a faint signature of negative mass. Telescopes are quietly looking. So far, nothing. And Hollywood got surprisingly close. For the film Interstellar, Kip Thorne, the same physicist, worked out how a real wormhole would truly look. A glowing sphere, not a hole. The science was so good, it led to published papers. So where does that leave us? Wormholes are allowed by our best theory of gravity, forbidden by no known law, and backed by exactly 0 observations. Gloriously, frustratingly open. Wormholes didn't arrive all at once. They crept into physics quietly, one discovery at a time. 1916, just months after Einstein published general relativity, Ludwig Flamm noticed the equations allowed a strange, tunnel-like structure. Nobody quite knew what to make of it. 1935, Einstein and Nathan Rosen formalized it, the bridge that now carries their names, a connection between two sheets of space-time. 1957, John Wheeler gave it the name that stuck: Wormhole. He also pictured space-time, at the tiniest scales, as a churning quantum foam, riddled with them. And 1988. Kip Thorne and his students worked out the first traversable wormhole, the kind you could, in principle, actually travel through. The dream became real physics. 70 years, from mathematical curiosity to maybe someday starship. Science is patient like that. To understand the far end of a wormhole, meet a black hole's strange twin. The white hole. A black hole is a place nothing can escape. A white hole is the exact opposite. Nothing can enter. It only spits matter and light outward, forever pushing everything away. On paper, an idealized wormhole connects the two. You fall into a black hole at one end and erupt out of a white hole at the other. The ultimate cosmic exit. There's just one catch. The math says white holes are wildly unstable. The moment anything falls toward one, it could collapse into an ordinary black hole. A door that slams the instant you knock. Some physicists have even wondered whether the Big Bang itself was a kind of white hole, the entire universe pouring out of a single point. Probably not. But what a thought! So far, we've never seen one. Which makes the white hole physics most dramatic maybe. Now for the strangest idea of all. It might tie wormholes to the deepest mystery in quantum physics. When two particles become entangled, measuring one instantly tells you about the other, even across the entire galaxy. Einstein hated it. He called it spooky action at a distance. In 2013, physicists Juan Maldacena and Leonard Susskind made a breathtaking proposal. What if entangled particles are connected by a tiny wormhole? They wrote it as an equation that reads almost like a riddle. ER equals EPR, wormholes equal entanglement. Two ideas from the 1930s, possibly describing the very same thing. If they're right, the consequences are staggering. Space itself might be woven together by entanglement. Pull the threads apart, and space-time could simply unravel. It's unproven, and fiendishly hard to test. But it hints that wormholes might not be exotic at all. They could be the very stitching of reality. A wormhole isn't the only way to cheat distance. There's a rival shortcut. The warp drive. The cosmic speed limit is simple. Nothing can move through space faster than light. But here's the loophole. Space itself has no speed limit at all. In 1994, physicist Miguel Alcubierre asked, what if you didn't move through space, but moved space around you? Squeeze it in front of your ship, stretch it out behind, and ride the wave. The ship sits still, while space does the traveling. So which wins? A wormhole punches a tunnel between 2 points. A warp drive surfs a bubble of bent space. Different tricks, same dream, crossing the galaxy without breaking the speed of light. And they share the same painful catch. Both demand exotic matter and negative energy in quantities we can only dream of. Two beautiful loopholes, both locked behind the same door. For now, the universe still says, not so fast. But notice, it never quite says no. Let's dream for a moment. Suppose a civilization did master wormholes. What would the universe become? Today, the stars are impossibly far. At the speed of our fastest probe, reaching the nearest one would take over 70,000 years. The galaxy is, for now, a prison of distance. But a network of wormholes would change everything. Anchor a mouth at Earth, another around a distant star, and the trip between them collapses to a single step. A galactic subway. Whole worlds could connect like stations on a map. A civilization spread across thousands of light years could feel as close-knit as a single city. It might even explain a famous puzzle. If aliens exist, where is everyone? Maybe advanced life doesn't crawl between the stars at all. Maybe it simply steps through. It's pure speculation, of course. But every road, every railway, every flight path began as exactly this, someone imagining the distance gone. Wormholes have starred in science fiction for decades. So let's see who actually did their homework. Interstellar. The wormhole is a glowing sphere with a far galaxy wrapped across its surface. Built with real equations from Kip Thorne. Verdict: astonishingly accurate. Star Trek and Deep Space Nine. A shimmering doorway that flares open, then politely vanishes. Gorgeous to look at, gentle on the physics. Verdict: fun, but a little too tidy. Stargate. Step through a ring and walk out on another world, instantly. The travel is basically a wormhole. The convenient lack of spaghettification, however, is doing a lot of heavy lifting. And the granddaddy of them all, Carl Sagan's Contact, the story that pushed Kip Thorne to work out traversable wormholes in the first place. Fiction didn't just borrow the science. It created it. Which is the real magic here. Sometimes a wild idea on a page is exactly where real physics begins. But there's a deeper problem lurking, one that troubles even black holes. It's called the firewall paradox. Quantum physics has one unbreakable rule. Information can never be truly destroyed. Whatever falls into a black hole, somehow, its information must survive. But Einstein's relativity says crossing into a black hole should feel like nothing at all. Just a quiet, invisible line you drift across. In 2012, physicists found these two ideas collide. To save the information, the edge of the black hole might have to become a wall of fire, incinerating anything that touches it. It's a war between our two greatest theories, quantum mechanics and relativity, and wormholes sit right in the crossfire. Some think the ER equals EPR idea might be the peace treaty. Nobody has solved it yet. Whoever does will likely rewrite physics and finally tell us what a wormhole truly is. Everything we've talked about hinges on one bizarre ingredient: negative energy. So let's ask the obvious question. Can we actually make it? Astonishingly, yes. A tiny bit. The Casimir effect we saw earlier really does create a region with less than zero energy squeezed between two plates. Certain laser tricks can do it too, briefly coaxing a sliver of empty space below the energy of the vacuum. For a fleeting instant, you've made nothing into less than nothing. But the universe guards this loophole jealously. Quantum laws insist that any pocket of negative energy must be quickly paid back, with interest, by an even larger burst of positive energy nearby. These are called the quantum inequalities. They don't forbid negative energy. They just make it borrow against the future, and the cosmic interest rate is brutal. So the door is open, just a crack. Whether it can ever be forced wide enough for a wormhole remains one of the great unanswered questions. We've assumed a wormhole connects 2 points in our universe. But the maths is far more daring than that. The same equations happily allow a wormhole to open somewhere else entirely. Not just a distant galaxy, but a completely separate universe. If the multiverse is real, a wormhole could be a doorway between bubbles of reality, each with its own stars, its own laws, perhaps its own kind of physics. Step through, and the constants of nature might shift beneath your feet. Gravity stronger, light slower, atoms that simply refuse to hold together. It's the wildest possibility of all, and almost certainly untestable. We may never know what waits on the other side, if there even is one. But that uncertainty is the point. A wormhole isn't just a shortcut. It's a question mark carved into the shape of the cosmos. So let's do it. Let's imagine, just once, what it would actually be like to cross. Ahead, the mouth hangs in space, not a hole, but a perfect sphere, the stars behind it bent into a glittering halo. You drift closer. The halo widens. The whole sky begins to wrap around you, two distant places folding into one impossible view. Then you're inside. Light streams past in ribbons. There is no falling, no wind, only the strange calm of space itself carrying you forward. And ahead, a new light blooms. Unfamiliar stars. A different sky. You cross the threshold, and a journey of 1,000 lifetimes ends in a single breath. It may never be possible, but for a moment, it's worth standing at the edge and imagining the step. You might be wondering, why spend a century on tunnels we may never build? It's a fair question, and the answer is beautiful. Because chasing wormholes forces our two greatest theories to confront each other. Quantum mechanics, ruler of the tiny. Relativity, ruler of the vast. Wormholes are where they meet and argue. Every attempt to understand them sharpens the deepest question in all of science. What really is space? What really is time? History is full of impossible ideas that quietly rewrote the world. Heavier than air flight. Splitting the atom. Talking instantly across the planet. Each was once pure fantasy. So the wormhole earns its place. Not as a promise, but as a lantern held up to the darkest, most wonderful corners of reality. And whether or not we ever step through one, the search itself takes us somewhere extraordinary. So, what if you fell into a wormhole? If the universe allows it, you could cross 1,000 light-years in a heartbeat, step out into another galaxy, maybe even another time. We can't build one yet. We have never found one. But nothing in physics says they are impossible. And in science, impossible is a very different word from undiscovered. If even a single wormhole is real, then distance stops being destiny, and the universe is far smaller and far stranger than it looks. I'm Foxmos. If you made it this far without being spaghettified, subscribe. There's a whole cosmos of questions left to fall into.